I recommend this method. You choose the one you like. X cubed plus x minus 2, everything squared. Let's differentiate the top. First function, top function. When you differentiate the top, you get 1 times the denominator minus. I copy the first function and I multiply it by the second one and differentiate it. So let's differentiate the second one. Can anyone give us the derivative of the denominator?
3x squared plus 1.
Excellent. Do we all agree with 3x squared plus 1? It would be a terrible mistake to try to simplify this x cubed plus x minus 2 with this. 1 from the factor. A factor from the denominator with terms from the numerator. Please do not do that. I know it's tempting. So I have to distribute in here using FOIL. So x cubed plus x minus 2 minus 3x cubed minus x minus 3x squared and minus 1. So I distributed x to 3x squared plus 1. And I distributed 1 to 3x squared plus 1. And now I combine like terms. I start with a degree, which is this. So this is negative 2x cubed. Then I continue with negative 3x squared. Luckily, these two go away, and then minus 3. Minus 3 over x cubed plus x minus 2 to the third. And this is it, but you know me, I'm going to pull out a negative leading coefficient. From, of course, from all of them. So this is the derivative of the given function, which was a quotient, or is a quotient. Is this okay?
I lost where the denominator became 3.
Yeah.
Yeah.
Can get away with anything. Sorry about that. I saw the 3 here and I copied 3 instead of 2. I'm sorry. Absolutely. I lost my mind for a second. Thank you for paying attention. No, I wasn't testing you. Make sure that you're paying attention. No. I just wrote 3 instead of 2. Good. So let's look at the product now. Any questions on this? And thank you for being so vigilant. Looking at the product, yes? No? Okay, number 9, on the same page, 189. U minus the square root of u, everything multiplied by u plus the square root of u. And you would say, yeah, multiply it and you get u squared minus u and get it over with. True. I'm not going to. Of course, I will always do that. But for this time, just this time, let's differentiate using a product. So this is function 1 and this is function 2, and we want h prime. Right? I will normally multiply and write this, and I'm done. And then I'll differentiate to u minus 1. We're never going to use the product rule on something like this, but we just want to practice the product rule. So please differentiate the first one, because remember we have 1 prime times 2 plus 1 times 2 prime. So let's differentiate the first function. What do we get?
1 minus 1 half u to the negative. So.
Yes, because that's the reason why we determined that the derivative of that function from the very beginning with the definition. So we never forget that the square root of u prime is 1 over 2 the square root of u. Is that okay? Good. Now times the second function, not differentiated. U plus the square root of u plus. I copied the first fraction, not fraction, but function, times the second function differentiated. What do I have?
1 plus 1 over
to the square of u. Excellent. A mess. Look at this. This would have taken 3 seconds. And look at this. Now I have to distribute, to simplify. I can't leave it like that. And I know the answer has to be 2u minus 1. This is a mess. But we just wanted to practice the power rule, the product rule. Why? Because when we get to the power rule combined with the product rule, we need to know how to apply the product rule. And when we get to the chain rule, which is going to teach us how to differentiate a function that is a function of another function. It could be a function of another function of another function of another function, etc., etc. I'll show you. Okay, so now I have no choice but distribute u to this, the square root of u to this, minus, I simplify and I get minus 1/2. Now 1 to these two, and plus u over 2 the square root of u, and this times this would be negative 1/2. Remember, the answer has to be 2u minus 1. Okay, so luckily these two go away, and also these two go away, and we get 2u minus 1, as expected. So far so good? We feel okay with this? Yes? Any questions? Any questions? Anyone? Okay, so I would like us to pick a problem in which we are given, suppose that blah, 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 blah. Very important, like 43 or 44. And I would like us to choose either 49 or 50, in which we read from a graph. So let's choose anything you'd like, 43, 44. Let's choose just one. 44, but A, B, C, or D. Let me enlarge this for you. Zoom in. So 44, A, B, C, D. D. Perfect. So let's copy the information. Okay, so they're telling us that f of 2, so this is 44 on page 190, f of 2 is negative 3, g of 2 is 4, f prime of 2 is negative 2, and g prime of 2 is 7. They're asking us to find h prime of 2, and we are given h of x, so this is only part D, is g of x over 1 plus f of x. So we're asked to find h prime of 2. So what do we have to find first in order to find h prime of 2? What is the first thing I need to determine? I'm asking you find h prime of 2. What would you ask me to give you? I'm saying, please evaluate function t of x for 3. What would you say?
What is t of x?
What is t of x? If I don't have t of x, how will I know what to do with it? How do I know how to find t of 3 or t of 5 or t of 10? Good. So in order to find h prime of 2, I have to find h prime first. Agreed? Good. Let's find h prime first. Let's do that. How do I do that? How do I find h prime?
x prime times 1 plus f of x.
Excellent. Minus.
Subtract, yeah. And copy the first one. And
Very
then
good.
do the prime of the second, with the new denominator.
Yes, when I differentiate 1, I get,
0.
so this is just f prime of x over 1 plus f of x to the,
Second.
that's it. I have the function. You can say you don't, because you don't have g and f. So what? I'm given the information I need. Now, because I have a formula for h prime, I can determine h prime of 2. What does h prime of 2 equal to?
So 7 times.
Yes, let me write it for everyone to see. Yes. 1 plus f of 2 minus g of 2 times f prime of 2 over 1 plus f of 2, everything squared. So this is very straightforward, right? Once you have the function, then you can use the given information and just plug it in. But remember, you have to make sure that you differentiate this correctly. Use any method you like, but if you reverse these two, the answer will be wrong. You can, if you want, you can reverse the order here in a product, but if you reverse these two and you put minus in front of this and plus in front of that, that will be incorrect. So careful. So now I will just replace them. So f of 2 is negative 3. So this is negative 3. This is negative 3. Then I have g of 2, which is 4. And g of 2 is 4. I have f prime of 2, which is negative 2. And I have g prime of 2, which is 7. So now I can put all these together and get a number. Because this is a number, not a function, correct? H prime of 2 will be a number. Will give us the instantaneous rate of change of that function h at 2. So h prime of 2 will be 7. 1 minus 3 is negative 2 minus 4 times negative 2 is negative 8, but with positive and with negative in front, it turns into positive. And then 1 minus 3 is negative 2, but negative 2 squared will be 4. So negative 14 plus 8 is, I think, negative 6 over 4, which is negative 3/2. So the slope of the tangent line to the graph of h at x equals 2 is negative 3/2. The instantaneous rate of change of this function, whatever the function represents, I don't know, is negative 3/2. Okay, the same thing. Are we interested, or we can move to something else? Are we interested to read from graphs or not? Yes? Okay, perfect. Excellent. I need my pencil. So I can, yeah, I have one in here. Perfect. Okay. So, which one? 49 or 50? 50, perfect. 50 it is. Part A or part B? Part A? Yes? Or part B? Which one? A, perfect. So, first of all, in order to determine P prime of 2, what do I have to find first? P prime. Here is P prime. I mean, here is P. And how do I determine P prime? So, P prime of x will be f prime of x times g of x, and plus f of x times g prime of x. Excellent. Good. And now I need to determine what happens at 2. So 2, 2, 2, 2, 2, correct? Good. Let's determine the easy ones. G of 2 and f of 2. Can anyone give us g of 2?
Nope, that's not. That's 2.
G of 2 is?
2.
2 indeed. Excellent. So this is 2. Can anyone give us f of 2? Very good. F of 2 is 3. Agreed with 3? F of 2 is 3? Okay. Now we want to determine f prime of 2. Here's f. Here's 2. What is f prime of 2 equal to? 0. The slope of a horizontal line is 0. Now we want to determine g prime of 2. At 2, I form a right triangle. Rise over run, and positive. How much? 1 over 2. So what is p prime of 2? Because this is 0, and this is 3 times 1/2. How much will it be?
1.5, 1.5.
Yes, so it's 3/2. Right. 3 over 1 times 1 over 2. P prime of 2 will be 3/2. Is that better? Okay. Any questions? So let me put it in writing just a tiny bit so you know what just happened. So this was problem 50 on page 190. So we were asked to find p prime of 2, and p of x was f of x times g of x. So therefore p prime of x is f prime of x times g of x plus f of x times g prime of x. And therefore p prime of 2, we determined those numbers. There was 0 times 2 and plus 3 times 1/2. This is 0, so this is 3 over 2. Any questions? Any questions? I want to talk about a theorem that, in my opinion, should be in this chapter. It's not. It's in chapter 4. But I would like to talk about it. It's called L'Hopital's rule. L'Hopital's, H is silent. L'Hopital's rule. L'Hopital's rule is applicable only in 2 indeterminate cases. 2. How many indeterminate cases we know exist? 7. How many did we look at so far? We saw so far 0 over 0, infinity over infinity, and infinity minus infinity. Okay. But L'Hopital's rule is applicable only in 2 indeterminate cases. Only in the indeterminate case 0 over 0 and infinity over infinity. And it's only applicable to limits. Only when we are determining a limit and the indeterminate case is 0 over 0 or infinity over infinity. Can you go back to your notes and just choose any limit in which the initial step by replacing x with or age or whatever the variable was in the problem, we replaced it with a number, and we got either 0 over 0 or infinity over infinity. So I can illustrate.
X squared minus 2x over x squared minus 4x plus 4. And the limit is x approaches 2.
2. Perfect. So we plug in, does the limit exist? I don't think it exists, but that's okay.
I thought you said 0 over 0.
That's fine. That's fine. But prepare one more example after this one. Okay, so we plugged in 2 in the numerator. and we got 0. Agreed? We plugged in 2 in the denominator, we got 0. In this particular case, L'Hopital's says this. L'Hopital's rule says this. Only inside a limit. Very important. Because if I ask you to differentiate this, what will you do? You will use the quotient rule. Top prime times the denominator minus the top times the denominator prime over the denominator squared. But this is not what we are looking at. We are looking at the limit of a function, and when we plug in, we get 0 over 0. In this particular situation or in this situation, one or the other, we are allowed to determine the limit by differentiating the top by itself and the denominator by itself. One more time, we never do this, ever. This is not the way we differentiate a quotient. But if a quotient is inside a limit, and the indeterminate case is this or this, only then we are allowed to differentiate the top as if it's by itself and differentiate the denominator as if it's by itself. So I have to write the limit. What is the derivative of the top? What is the derivative of the denominator? Good. What do you expect? It's a good one. What do you expect to do next? Right? You would say just factor the top, factor the bottom, blah blah blah. We know what is the factor that creates the problem. What is the factor that creates the problem?
X minus 2.
X minus 2. Assuming we don't know that, I plug it in again, and what do I get at the top? Yes. What do I get in the denominator, however? Right. And I have to stop. Because 2 over 0 is not a situation in which I can apply L'Hopital's rule again. So was it 2 from the left or 2 from the right?
From the left.
Okay, sorry. So in that case, I will simplify. I have to go back to the original method that we discussed a long time ago. So I have limit as x approaches 2 from the left, 2x minus 1 to x minus 2. I simplify, and the numerator 2 from the left is 1.9, so this is positive, and 2 from the left, 1.9, and this is negative, and that's how we get negative infinity. But I wanted an example in which the limit exists, so I can illustrate L'Hopital's rule again, or I will find one. It's an extremely helpful method. So I'm going back to the end of chapter 2. We couldn't have used this on this test because we didn't know differentiation rules. And you don't really want to find the derivative of that function with the definition, the top and then the bottom, and no, you don't want to do that. So, for example, let's look at this one, number 4. X approaches 3. So this is problem 4 on page 167. And we have limit as x approaches 3. The numerator x squared minus 9. The denominator x squared plus 2x minus 3. Remember, this is crucial. If this is not 0 over 0 or infinity over infinity, L'Hopital's rule is not applicable. So does the numerator go to 0? Does the denominator go to 0? Did I copy it correctly? If the denominator does not go to 0, we cannot use L'Hopital's rule.
No, it doesn't.
In that case, so this is 9 minus 3 is 6, and 6 plus 6 is 12. So the answer is 0. It's a very good counterexample. We cannot use L'Hopital's rule if it's not 0 over 0, infinity over infinity. I found another. 8 on the same page. Limit as t approaches 2 from t squared minus 4 over t squared, t cubed minus 8. This requires a lot of work, right? You know it's 0 over 0 because 4 minus 4 and 8 minus 8. So, but if you want to determine the limit using the methods we discussed, which is the only one is factoring, right? You would have to factor the difference of cubes and the difference of squares, and then eliminate for sure which factor that creates 0 over 0, for sure. T minus 2, right? Good. But it's 0 over 0. Let's apply L'Hopital's rule. And this is very straightforward, very simple. The numerator is, the denominator is, good. I simplify, although I can continue. Let's say we don't simplify. 2 over 3 goes outside, it's a factor. I don't care for it. So I have t over t squared. What now? Let's say we don't simplify. We don't know how to simplify. Is it still 0 over 0? No. So just plug it in. So 2/3 multiplied by 2 over 4. Bless you. So these two go, all these three go, and it's 1/3. The work is tremendously reduced. Otherwise, you would have had to factor the difference of cubes and simplify and then plug it in. However, it has limited applicability, though. These are the only cases. However, the other cases, except infinity minus infinity, can be changed into these two, and you will see in a later section. So all the others that we haven't even seen, we will be able to change them into one or the other. And we will end up applying L'Hopital's rule. Okay, this theorem is, or L'Hopital's rule is in chapter 4, but I can't really wait till then.
Oh, wait, so if we encounter like something like this for this section,
Oh, absolutely. Moving forward, you can use it anytime from now on. If it's applicable, please use it on any limit. And I'm going to use it in a minute. Okay, so I still have 15 minutes, so allow me to continue with derivatives of trig functions. Say it again. In the past, I always ask my students if they want to see a proof of sine prime or cosine prime. So I'm going to ask you the same. It's not a very short proof. We can work through it if you'd like. And then the rest of trig functions will be, we're going to use the quotient rule, because all the other ones are like tangent and cotangent are ratios of two trig functions. Secant and cosecant we can't till we look at the, or we can use the quotient rule, actually. We can. We don't have to use the chain rule. Okay, it's up to you if you'd like to see, of course, with the definition. What is the definition for any of them? So f prime of x for the top, limit as h approaches 0, sine x plus h, of course, minus sine x over h. So we can go through a proof, one or the other, or say, let's save the time and continue with all 6 trig functions. It's up to you. You want to save the time?
Yeah.
Okay, in that case, you just have to trust me that sine prime is cosine, and cosine prime is negative sine. Now the rest, tangent, cotangent, secant, cosecant, let's determine them because we can. That's the easy part. So I will write tangent x as sine x over cosine x. And in order to determine tangent prime, we're going to differentiate sine x over cosine x. This is not inside a limit, so please do not get confused on that. It's not inside a limit, so we have to use the quotient rule. And I'm ready when you are.
Cosine
So, exactly.
times cosine
Very good. Minus
sine x
times,
negative sine x.
I'm going to change this, over cosine squared. Is that clear what happened with that negative in front? Because we had the negative from the formula and we had a negative from cosine prime. So can anyone tell us what we have at the top? Obviously we have
Cosine
squared plus sine squared, and we know what that is. How much? Exactly, thank you very much. And we also know that 1 over cosine is what trig function. If the denominator has c in it, the function starts with s. If the denominator has s, the function starts with c. Excellent, excellent, yes. Secant squared x. So moving forward, we add this to our list. In the same way for cotangent prime, we have negative cosecant squared. But for secant prime, we get secant x tangent x. And for cosecant prime, we get negative cosecant x cotangent x. We can prove any of these using differentiation rules, not the definition. Okay. A while back, we looked at this limit. And I said I cannot show you why, algebraically or by hand, but I showed you this limit with a graphing calculator by graphing the function sine x over x. Anyone remembers what this is equal to? It's a very important limit. I did not show the graph of sine x over x. Okay, let's do it now. Okay, thank you very much. So we did look at the graph, yes? Okay, perfect. Please plug it in and tell me what you have. No, plug in 0 and tell me what this is. Good. What does that mean? L'Hopital's rule. 0 over 0 is a totally indeterminate case we cannot conclude. But it's 0 over 0, now I can apply L'Hopital's rule. So this is limit as x approaches 0. The derivative of the top is, we couldn't do this before because first of all we didn't know differentiation rules and we did not know L'Hopital's rule. And the derivative of the denominator is, so then the limit is, and I don't care for the graph anymore, indeed. When x approaches 0, cosine approaches 0, approaches 1. Now we know why that is the case. However, this limit is so important that it can be applied in many situations. So this is how we have to look at it. as long as all these pieces are identical. And this piece, whatever that is, approaches 0. This could be x minus 1, this could be x minus 1, this could be x minus 1. X minus 1 approaches 0 means x approaches 1. This could be x cubed plus 1. This could be x cubed plus 1, and this could be x cubed plus 1 when x approaches 1. A negative 1, so on and so forth. As long as all these are identical and this quantity approaches 0, the answer is always 1. If any of these is different, is not identical, then the limit is not 1. So I would like us to, I know we have 6 minutes left, I would like us to look at a limit. Yes, we can get away, so now we're going to be able to make more progress with the handout, with the limits. So I'm looking on page 198, and I would like to start with this problem, 48. So in 48, on page 198, we have limit as x approaches 1 from either side, from sine x minus 1 over x squared plus x minus 2. We do not know how to differentiate a function of a function. So yes, it is 0 over 0, but at this point we have one more section to go through, and then we'll be able to differentiate the numerator. Right now we can't. So don't use L'Hopital's rule. We can't just yet. But I see that this piece, of course it's 0 over 0. This piece, because x approaches 1 means x minus 1 approaches 0. Same thing. This and this are the same. And here I can factor the denominator into, indeed. So now I know that since these 3, 1, 2, 3, are the same, what is the limit of this piece? See, I still have x plus 2 in the denominator. Where is this going? This is going to 1. But then where is 1 over x plus 2 going when x approaches 1? 1 over 3, indeed. So we were able to do this because we know that the limit of sine of the same quantity over the same quantity when this quantity approaches 0 is 1. Yes, I'll stop. Just one more example. I promise to stop after this one. So I would like us to differentiate. You want a quotient or a product with trig functions? Quotient, number 12, on page 197. So we have y equals cosine x over 1 minus sine x. I promise to stop after this. So then y prime, the top prime, negative sine x in parentheses 1 minus sine x minus cosine x, and then times. So negative is from the formula. I copied the first function, and now I have to differentiate this, which is indeed negative cosine with this. Yes, I'm going to change it into positive. Excellent.
Okay.
Well done. So then, negative, I distribute. Negative sine x plus sine squared x plus cosine squared x over 1 minus sine x squared. But sine squared plus cosine squared is?
That's
1 minus sine x over 1 minus sine x squared. And the simplified form is of this derivative?
1/1 minus.
Yes, 1/1 minus sine x. That's exactly it.